Welcome to Chapter 5, Section 4, Lopital's Rule. In the previous sections, we built up the machinery of differentiation and proved the mean value theorems. Now we put that machinery to work on a very practical problem, evaluating limits of quotients where both the top and the bottom rush to zero, or where the bottom blows up to infinity. These are the famous indeterminate forms, and Lopital's rule turns them into a routine calculation, replacing the quotient of two functions by the quotient of their derivatives. In this episode, we state the rule precisely in the general form given by Rudin, and then we prove it carefully using the generalized mean value theorem from Section 2. Let's dive in. Here is the plan for this episode. We begin with motivation, the problem of indeterminate forms, expressions like 0 over 0 and infinity over infinity, where naive substitution tells us nothing. We then state Theorem 513, Lopital's rule, in full generality, and unpack what its hypotheses really say. After building geometric intuition for why differentiating the top and bottom should help, we walk through the proof, step by step. The engine of the proof is the generalized mean value theorem. Finally, we summarize the key points, note an important warning about where the rule fails, and preview what comes next. Let's set the stage. Very often in analysis, we need the limit of a quotient f of x over g of x, and when we try to substitute directly, both the numerator and the denominator go to 0. Writing 0 over 0 is meaningless. It is what we call an indeterminate form. The ratio could tend to any number at all, or to infinity, or fail to have a limit, depending entirely on how fast the top and bottom shrink. For instance, x divided by x tends to 1, while x squared divided by x tends to 0, and x divided by x squared runs off to infinity, even though all three have the bare form 0 over 0. So substitution alone cannot decide the answer. We need a better tool. The 0 over 0 case is not the only troublemaker. A closely related situation occurs when the denominator g of x tends to plus infinity. Then the quotient has the shape something over infinity, and again the outcome is not determined by inspection. The numerator might also blow up, and the competition between them decides the limit. Rudin handles both of these cases with a single theorem, which is one of the nice features of the general statement we are about to see. Here is the guiding idea. If both functions vanish at a, then near a, each one is controlled by its rate of change, its derivative. Replacing each function by its tangent line approximation, the numerator is roughly AWF prime of a times the quantity x minus a, and the denominator is roughly g prime of a times the same quantity. That common factor cancels, leaving the ratio of the derivatives. This is only a heuristic, but it is exactly the right intuition. The limit of the quotient should equal the limit of the quotient of derivatives. Lopital's rule makes this precise, and remarkably, it needs no continuity of the derivatives at all. Let's look at the classic example. The most famous instance is the limit of sine of x over x as x goes to 0. Both the top and the bottom vanish at 0, so it is a 0 over 0 form. Taking the derivative of the top, cosine of x, and of the bottom, 1, the quotient of derivatives is cosine of x over 1, which tends to 1, so the original limit is 1. This also matches a familiar geometric fact. For a small angle, the sine of x is very nearly x itself, so their ratio sits close to 1. The picture shows the graph of sine of x over x in amber. Away from the origin it dips and oscillates, but as x approaches 0 from either side, the curve rises smoothly to the height 1, marked by the dot on the vertical axis. There is no actual spike or hole in the limiting value. The function fills in to 1. We are borrowing the derivatives of the trigonometric functions here, which we will justify in Chapter 8, just as the book does. Now let's state the theorem in full generality. Here's the theorem. Suppose f and g are differentiable on the open interval from a to b, and the derivative of g is never 0 there. The endpoints a and b are allowed to be infinite, which is why the rule handles limits at infinity too. The crucial hypothesis, labeled 13, is that the quotient of derivatives f prime over g prime tends to a limit a as x approaches a. Then, provided either condition 14 holds, where both f and g tend to 0, or condition 15 holds, where g tends to plus infinity, the original quotient f over g also tends to the same value a. The practical payoff is that we may trade a hard quotient for the often simpler quotient of derivatives, and the one thing we must check is that this derivative quotient actually has a limit. So the two indeterminate forms from the motivation are covered by one clean statement. Let's read the two cases side by side. It is worth pausing on the two cases. On the left is the 0 over 0 form. Both f and g tend to 0, and the conclusion is that their ratio tends to a. On the right is the infinity case. Here we only require that g tends to plus infinity. Notice something surprising about the right-hand case. We assume nothing whatsoever about the numerator f. It does not have to tend to infinity, or to 0, or to anything in particular. The single assumption that the denominator blows up, combined with the hypothesis on the quotient of derivatives, is enough. Both cases deliver the same conclusion from the same key hypothesis, condition 13. Let's watch that infinity case in action. Let's watch the infinity case at work. Take the logarithm of x divided by x, as ex tends to plus infinity. Both the top and the bottom grow without bound. So this is the infinity form handled by condition 15. Differentiating, the top becomes 1 over x, and the bottom becomes 1. So the quotient of derivatives is 1 over x, which tends to 0. Hence, the original quotient tends to 0 as well. The amber curve on the slide tells the same story. It climbs to a small hump near the left, and then decays steadily back toward the horizontal axis, showing that x eventually outruns the logarithm. This is the precise sense in which logarithmic growth is slower than linear growth. And notice, in keeping with case 15, we only needed the denominator to blow up. We placed no condition on the numerator. Now a few remarks on the fine print. A few remarks round out the statement. First, everything we say for the limit as x approaches the left endpoint a has a mirror image for the limit as x approaches the right endpoint b, and the infinity case works just as well if g tends to minus infinity instead of plus infinity. Second, all these limits are understood in the extended sense of definition 4.33 from Chapter 4, which means the target value a is itself allowed to be plus or minus infinity, not just a finite number. Finally, the assumption that g prime is never 0 is more powerful than it first appears. Recall from the previous section that a derivative has the intermediate value property, theorem 5.12. So g prime cannot be positive at one point of the interval and negative at another, because then it would have to pass through 0 somewhere in between, which we have ruled out. Therefore, g prime keeps a single sign on the whole interval. Either it is positive everywhere, or it is negative everywhere. Either way, g is strictly monotonic, so it takes distinct values at distinct points, and every denominator we form in the proof is non-zero. With the statement understood, let's see the geometry behind it. Before the formal proof, here is the strategy. The whole argument is a two-sided squeeze. We show that the quotient f over g eventually lies below every number u that is bigger than a, and by a symmetric argument that it eventually lies above every number p smaller than a. Together, these trap the quotient as close to a as we like. The bridge from the hypothesis on derivatives to a statement about the functions themselves is the generalized mean value theorem from section 2. That is the step that makes derivatives talk to function values. Steps 3 and 4 are where the two cases, 0 over 0 and the infinity case, are actually used. Let's first recall the tool that powers step 2. The engine of the proof is theorem 5.9, the generalized mean value theorem. It says that for 2 points ex and y, there is some intermediate point t where the ratio of the differences f of ex minus f of y over g of x minus g of y equals the ratio of the derivatives at t. The picture makes this geometric. Think of the pair g of t and f of t as tracing a curve in the plane shown in blue. The two amber points are the endpoints, and the amber line joining them is the chord. Its slope is exactly that ratio of differences. Theorem 5.9 promises a point on the curve, marked in red, where the tangent line runs parallel to the chord. The slope of that tangent is the ratio of the derivatives f prime of t over g prime of t. Intuitively, the average rate of climb measured across the chord must be matched by the instantaneous rate at some point in between. So a bound on the derivative ratio becomes a bound on the chord slope. Now we begin the proof. Step 1. We handle the case where a is less than plus infinity. The other case is symmetric. Fix any number q larger than a and squeeze a second number r strictly between a and q. Because the quotient of derivatives tends to a and r is above a, the quotient is eventually below r. Concretely, there is a cutoff point c, so that for every x between a and c, the derivative ratio f prime over g prime is less than r. This is inequality 17. Next, we push this bound from derivatives onto the functions. Step 2 applies the engine. Take 2 points x and y with x below y, both to the left of the cutoff c. The generalized mean value theorem gives an intermediate point t where the ratio of differences equals the derivative ratio there. But t lies to the left of c, so by step 1 that ratio is below tr. This yields inequality 18. The ratio of the function value differences is less than r. This is the key move of the proof. We began with information about derivatives, and we now have a clean inequality about the functions themselves. From here, the two cases diverge. Step 3 treats the 0 over 0 case. Condition 14. In inequality 18, hold y fixed and let x slide toward the endpoint a. Both f of x and g of x go to 0, so the left-hand side becomes 0, minus f of y over 0 minus g of y, which is just f of y over g of y. The strict inequality relaxes to less than or equal in the limit, giving inequality 19. F of y over g of y is at most r, hence below q, for every y between a and c. So the quotient is already bounded above by q. Now the harder infinity case. Step 4 is the infinity case, condition 15, and it takes a little algebra. This time we keep y fixed and use that g of x tends to plus infinity. So for x, close enough to a, say to the left of a new cutoff, c sub 1, the value g of x is positive and larger than g of y. That makes the factor g of x minus g of y, all over g of x, a positive number. Multiplying inequality 18 by this positive factor preserves its direction, and after rearranging, we arrive at inequality 20. On the right, we now have r, plus two correction terms that both carry a g of x in the denominator. Watch what those correction terms do as x approaches a. Continuing step 4, look again at inequality 20. The number y is fixed, so f of y and g of y are constants, while g of x marches off to infinity. Both correction terms therefore shrink to 0, and the right-hand side approaches r, which is below q. So there is a still smaller cutoff, c sub 2, beyond which the quotient f of x over g of x is less than q. That is inequality 21. Notice that both cases have now landed in exactly the same place. Whether we are in the 0 over 0 situation or the infinity situation, we have shown that for any q bigger than a, the quotient is eventually less than q. Only the lower bound remains. Step 5 closes the argument by symmetry. The same reasoning with the inequalities reversed shows that for any number p below a, the quotient eventually exceeds p. That is, inequality 22. Combining this with the upper bound, given any p below a and any q above a, the quotient is eventually caught strictly between them. The number line at the bottom pictures exactly this. The target a is the red mark in the middle. The two blue markers are the bounds p and q, and the shaded band is where the quotient finally lands. Since p and q can be pushed as close to a as we please, shown by the amber arrows closing inward, the quotient must tend to a in the extended sense. The proof is complete. Let's gather the takeaways. Let's review. The star of this section is Theorem 513, Lopital's rule. Its message is simple to remember. If the quotient of the derivatives tends to a limit a, and if we are in one of the two indeterminate situations, either both functions tend to 0 or the denominator tends to plus infinity, then the quotient of the original functions tends to the same limit a. This converts a hard limit into an often easier one. The proof was not just a formal manipulation. It rested on one central idea. The generalized mean value theorem from section 2 is what lets us convert information about the derivatives into information about the functions. Everything else was a careful two-sided squeeze, trapping the quotient between an arbitrary number below a and an arbitrary number above a. This pattern bound the derivative, transfer with the mean value theorem, then squeeze, recurs throughout analysis. A word on how general this really is. The endpoints a and b are allowed to be infinite, so the rule covers limits at infinity, not just at finite points. The target a may also be infinite, and recall the striking feature of the infinity case. When the denominator blows up, we need no assumption at all on the numerator. These are not decorations. They are what make the theorem so widely applicable. But there is one important limitation to flag. The final and most important caveat. Lopital's rule is a theorem about real-valued functions, and it genuinely breaks down for complex or vector-valued functions. We will meet a concrete counterexample later in the chapter, in example 5.18, where the quotient of derivatives tends to 0, but the quotient of the functions does not. The reason traces back to the mean value theorem itself, which also fails in that setting. So keep the rule in its lane, real functions only. In the next episode, we turn to derivatives of higher order and build toward Taylor's theorem, which approximates a function by a polynomial and estimates the error. See you there.